what we were looking at was we had the function y of t, right? And what we were trying to do is we wanted to get Laplace transform of y of t, right? So if you have this arrow over here to indicate Laplace, right? What you were given is the y of t, and what you're trying to do is you're trying to figure out the Laplace transform of y of t, right? So over here, I had the y of t here, right? And what we wanted to do is we wanted to figure out what Laplace transform of y of t, right, is, right? Notice this here is a function of s, right? Okay, so now what we want to do is we want to consider your reverse problem, right? Okay, so the idea here was that given the function y of t, right, we were trying to determine its Laplace transform, right? That is what we were doing previously, right? And now what we want to do is we want to consider your reverse problem, right? If you're given a function of s, right? What you want to do is you want to see if you can get a function of t such that when you take Laplace transform of it, you actually get the function y of s, right? So what you're doing is you're working backward in a sense, right? You still have this Laplace over here, but now what you have is you have the function of s given to you, right? And what you're trying to do is you're trying to figure out what the function of t is, right? Right, so an example of that is this over here, right? Okay, so here I have this function y of s, which is 2 on s squared plus 4, right? And what I'm trying to do is this here, suppose this arrow here is supposed to indicate Laplace, right? And what I'm trying to do is I'm trying to figure out, well, what is the function y of t, right? What's the function y of t that when I take Laplace transform of it, I get this 2 on s squared plus 4, right? And how we're going to do this is basically you're going to do this by recognition, right? Okay, but before I get into more details into this example, let's just get some notation for going backward here, right? So okay, so the situation now is I have your function y of s such as this 2 on s squared plus 4, right? And what I'm trying to do is I'm trying to figure out the y of t, the function of t, such that when I take Laplace of it, I get this 2 on s squared plus 4, right? Okay, so this is y of s over here, right? Y of s, right? What I'm trying to do is I'm trying to determine a y of t such that Laplace of y of t is equal to y of s, right? So I need to figure out what y of t is on this left-hand side, right? Okay, and if you have a function of s and you can in fact figure out what the y of t is, right? Then what you call this y of t is you call it the Laplace inverse of y of s, right? Okay, so this is the y of s over here. And if you can figure out what the y of t is, right, then that y of t is called the Laplace inverse of this 2 on s squared plus 4, right? And your notation is this, right? Right, so function of s that is, in this case, now given to you, right, such as 2 on s squared plus 4. If you can work backward and get the function of y of t such that when you take Laplace of y of t, you get y of s, right? Then what the small y of t is called the Laplace inverse of y of s, right? Okay, so let's look at an example here, right? I have this function y of s, which is 2 on s squared plus 4, right? And what I want to do is I want to get the inverse Laplace transform of this function y of s here, right? Okay, so remember what I'm trying to do, right? This is the y of s over here. So getting the inverse Laplace transform means I'm trying to figure out what the y of t is, such that when I take Laplace transform of it, I get this y of s, right? Okay, now how do I do that? Well, really, I just do it by recognizing the form, right? This is the first approach that we would have for getting inverse Laplace transform, right? You want to recognize the form of this function of s here, right? Okay, so I have this 2 on s squared plus 4, and then you look in your table and you see if anything is of that form, right? Okay, so it's not, well, it's not this one over here, right? It's not 1 on s minus a because what I have is an s squared, right? It's not going to be, say, these over here. Here I have s squared minus, and here this is s squared plus, right? So the only two that could potentially work for me would be these over here, right? here I have s squared plus, and here I have s squared plus a constant, right? And notice here I have s squared plus a constant, right? Okay, so when you're doing inverse Laplace transform for, say, a simple one like this, right? Usually the key thing that you're starting with is your denominator here, right? You look at the denominator here, which is s squared plus 4, and you compare it to your denominators in your table, right? Okay, so here I have s squared plus a constant, and here I have s squared plus a constant, right? So I narrowed it down to these two over here, and now you want to notice that what I have is I have a constant on top here. Here I have an s on top here, and here I have a constant on top here. So this one would suit me, it would work better for me, right? Okay, so what I notice is that sine kt, the Laplace transform of sine kt is k on s squared plus k squared, right? And I wrote it down over here, right? Laplace of sine kt is k on s squared plus k squared, right? Okay, so that gives me an indication that, well, this is the formula that I'm going to be using, right? And well, note, all I need to do now is just choose a suitable value for this parameter small k over here, right? And what I want to do is I want to choose a parameter for the small k so that I get s squared plus 4 on the bottom, right? Okay, and if I use the small k, if I set this small k to be equal to 2, right? Then what I'd have is I'd have s squared plus 4 over here, and I have a 2 over here, right? On top, right? So what I see is Laplace of sine 2t is equal to 2 on s squared plus 4, right? And this is what I want, right? The 2 on s squared plus 4 is the y of s, right? Okay, so the 2 on s squared plus 4, that is what you're given, right? And what you're trying to do is you're trying to figure out the y of t, right? And this y of t, right, in order for Laplace of y of t to be equal to y of s, right, this y of t over here would need to be sine 2t, right? So what that means is that when you go backward, what this needs to be over here is this needs to be sine 2t, right? Can't be anything else, right? Well, at least for this class, right? Okay, so your inverse Laplace transform of your 2 on s squared plus 4, right? What it's going to be is going to be this y of t over here, and the y of t will have to be the sine 2t, right? Okay, and how you're going to write this is Laplace inverse of the 2 on s squared plus 4, right? So the Laplace inverse of this 2 on s squared plus 4 is sine 2t, right? Or you could look at it from here, right? What I'm trying to do is I'm trying to get inverse Laplace transform of 2 on s squared plus 4, right? From the table, I get that Laplace of sine kt is k on s squared plus k squared, right? How I know to use this one, right, is really I'm just recognizing the form over here, and in particular looking at the denominator, right? So I look in the tables and see that this is the most suitable one to use, right? Okay, and then I want to use the appropriate constant, and the appropriate constant over here would be small k is equal to 2, right? And what I get is Laplace of sine 2t is 2 on s squared plus 4, right? Okay, so the function of t that would give me 2 on s squared plus 4. In other words, the inverse Laplace transform of the 2 on s squared plus 4 would be what's inside over here, which would be the sine 2t. Alright, and recall that we saw previously when looking at Laplace transform, so just normal Laplace transform, is that if I have a sum of functions of t with constants over here, I can break up with the sums, I can break up according to the plus, right? And I can pull constants out, right? And that is using linearity property of the Laplace transform, right? So for example here, with this Laplace of t squared plus 3t plus 2, right? This I can work out as Laplace of t squared plus Laplace of 3t plus Laplace of 2, and then I can always pull constants out, right? Okay, so that's when I'm trying to figure out Laplace transform, right? And it turns out that inverse Laplace transform also has a similar property, right? It also has linearity property. So if I'm going to take Laplace inverse of a sum, right, I can actually break up the sum, and then I can also pull constants out, right? So this is what the statement is over here, saying over here, right? When I'm calculating Laplace inverse, I can actually break up the sums and pull out constants. Alright, so let's see an example of taking inverse Laplace transform of when I have a sum, right? And when I can pull constants out, right? So when I take Laplace inverse of this sum over here, right? Okay, so it's going to be, so I have Laplace inverse of the sum, and I said that so this is what I want to work out, Laplace inverse transform of this sum over here, right? And I said that I can, if I have the sums inside there, right, I can take Laplace inverse of the individual pieces and then just add them up, right? So this Laplace of your sum inside here is Laplace inverse of the s on s squared minus 9 plus Laplace inverse of 2 on s to the fourth, and then plus Laplace inverse of 11 on s squared plus 5, right? Okay, so and notice why you want to do that, right? Why you want to do that is you're breaking it up into smaller pieces. This entire thing over here, right? This big sum over here is not going to come directly from your table, right? You're not seeing it over here in your table, right? But the smaller pieces here, right? In this case, your smaller pieces over here, you can in fact use your table, right? Okay, so I have Laplace inverse of say this s on s squared minus 9, right? Okay, so this s on s squared minus 9, you look in your table and you notice that, well, what I can use is I can use this over here, right? Okay, so Laplace of hyperbolic cosine is equal to s on s squared minus k squared, right? Which means that Laplace inverse of the s squared, the s on s squared minus k squared is the hyperbolic cosine, right? So if I'm going backward over here for this, right, what I'm going to get is, if I'm going backward, right, from the s to the t, right, what I'm going to get is a hyperbolic cosine. And I just need to figure out what the constant k is over here, right? Okay, so notice over here what I have is that the parameter is equal to 3 over here, right? And if your parameter is equal to 3 over here, it means that the parameter would have to be 3 over here, right? Or in other words, Laplace of hyperbolic cosine of 3t is s on s squared minus 3 squared, which is what I have, right? Okay, so Laplace inverse of the s on s squared minus 3 squared is going to be hyperbolic cosine of 3t, which is what I have over here, right? Okay, so that's this piece over here, right? So notice this piece here just came from the table, right? And now each of these are going to come, the remaining two are going to come from the table, but you'd need to adjust the constants a little bit, right? Okay, right. Now what I have over here is 2 on s to the fourth, right? I want to get Laplace inverse of 2 on s to the fourth, right? Well, okay, so, well, what is this? Which one of the formula in the table can I use, right? Well, it's not going to be these over here because, well, this is s squared plus something and s squared minus something. This is s minus something, right? It's not these over here, right? What it's going to be is what I have is s star power, right? And when I have s star power on the bottom, I'm using this here, right? Okay, so I have s star power. So this is the formula that I'm going to use, right? So what this means is that Laplace inverse of this 2 on s to the fourth, right, is going to be some power of t over here, right? I just need to figure out what the power of t is, right? And then probably adjust it by a constant, right? So which we'll see in a second, right? Okay, now the key thing in determining the power, right? And as I said, what you want to do is you really want to focus on your denominator over here, right? On the denominator, what you have is s to the fourth here, right? So the power is equal to 4, right? Okay, so in order to have s to the fourth over here, the small n would have to be equal to 3, right? Okay, so this is 3 over here, and, well, if this is 3 over here, I'd need 3 factorial on top, right? Okay, so I have 3 factorial and s3 plus 1, which is 4, right? So 3 factorial and s to the fourth, right? Okay, but the problem is what I have over here is 2 on s to the fourth, right? I don't have a 3 factorial on top here, right? Alright, so looking at this Laplace inverse of the 2 on s to the fourth, right? What I'm going to use this formula here for Laplace of t to the n, right? And the fact that I have s to the 4 over here means that I'm gonna use small n is equal to 3, right? So I'd have 3 over here, 3 plus 1, which is 4, which means I'd want a 3 factorial on top, right? But the problem is what I have is over here is 2 on s to the 4th, right? Okay, so how do I deal with that, right? Well, I want a 3 factorial, right? So what you do is you put a 3 factorial on the top and a 3 factorial on the bottom, right? And notice you didn't change anything because 3 factorial on 3 factorial is just 1, right? Okay, so and now what you do here is I can pull this 2 and 3 factorial outside, right? And I have what I'm left with is Laplace inverse of 3 factorial on s to the 4th, right? Okay, so I managed to get the, in my formula here, I get the n is equal to 3 and s is equal to 3 plus 1, right? Which means that this is going to correspond to Tn, where the small n is equal to 3, right? Okay, so the key thing over here is I'm able to write this 2 on s to the 4th as with the appropriate factorial on top, right? 3 factorial on s to the 4th. But I needed to adjust the constants. And when I adjust the constants, I needed to pull a 2 on 3 factorial outside, right? And how I did it is via this adding the factorial on the top and the bottom over here, right? Okay, but I have equality. This is 2 on s to the 4th, and likewise, this is still 2 on s to the 4th, right? Anyway, so I get to this point. This is 2 on 3 factorial. Now, 2 on 3 factorial is 2 on 6, which is 1 on 3, right? So what I have is 1/3 over here, right? So I get 1/3 over here. And then this one over here works out to be t cubed, right? Okay, so that is how I'm going to deal with this Laplace inverse of the 2 on s to the 4th, right? First thing I do is I write it using a 3 factorial on s to the 4th, right? I needed to add in the extra 3 factorial on the bottom to maintain equality. Pull out the 2 on 3 factorial and then just use your formula for Laplace inverse of the 3 factorial on s to the 4th. And I'm just left. Okay, so I still have this Laplace inverse of 11 on s squared plus 5 to deal with, right? Okay, so well, first thing I should probably try to do is realize, well, what which function from my table am I going to use, right? So here I have s squared plus a constant, right? So I have s squared plus a constant over here, and then I have a constant on top. So I have a constant on top over here, right? Okay, so that is giving me an indication that what I'm going to be using is I'm going to be using my formula for Laplace of sine kt, right? Okay, so when I'm taking my Laplace inverse, I'm going to adjust the constants over here so that the function of s is going to look like this over here, right? Now, in particular, notice over here I have 5, and here I have k squared, right? So I need to deal with that, right? And how I deal with that is this here, right? Okay, so this is what I want to get when I get Laplace inverse of this 11 on s squared plus 5, right? Okay, so and recall what I want is I want something squared over here, right? So here what I had was k squared here, right? So what I want is something squared here, right? Now the 5 over here, I can always write as square root of 5 squared, right? It's the same thing, right? Square root of 5 squared is just equal to 5, right? So I just rewrote this 5 to write it as something squared, right? Okay, now the next thing you want to notice is that if I have s squared plus k squared over here, what I would need is the k on top over here, right? So I need a square root of 5 on top to directly use my formula, right? So if I have k squared over here, I have need k on top over here, right? And in this case, the k is square root of 5, right? So if I have square root of 5 squared here, I need square root of 5 on top, right? Okay, so what I'm going to do is I'm just going to adjust the constants a little bit, right? I'm not changing anything, right? I'm just rearranging it, right? Notice here, what I have is 11 on root 5 times root 5, right? Now this root 5 on the bottom will cancel with the root 5 on top. So I still have 11 on top as I do over here, right? And now what you could do is you can pull this 11 on root 5 outside using the linearity, right? So have 11 on root 5 and now Laplace inverse of this expression, right? So that's how I go from this line here, from this expression to the 11 on root 5, Laplace inverse of square root of 5 on s squared plus square root of 5 squared, right? Okay, and now that I have that, right, this Laplace inverse is just going to come directly from the formula for Laplace of sine kt, right? In this case, the small k is equal to square root of 5. So Laplace inverse of square root of 5 s squared plus square root of 5 squared is sine of square root of 5t, right? Okay, so this here, Laplace inverse of it is sine square root of 5t, right? And this gives me my answer, right? Okay, so to overview, right? If I have Laplace inverse of a sum, right? In this particular case, what I do is I break it up into Laplace inverse of the smaller functions of s, right? And then each of these are going to come directly from the table. This one comes directly from the table, right? But these over here, while they're going to come from the table, right? These two over here, they need adjustment for the constants, right? So I needed, instead of 2 over here, I needed 3 factorial, right? And I adjusted the constants here, right? Notice there is equality, it's just an adjustment of constants. And also over here, right, this is going to come from a formula for sine kt, but I needed to adjust the constants, right? So for this one over here, it was just directly using the formula, but for these two, I was using the table, but I needed to just adjust the constants a little. Okay, so we saw the Laplace inverse of this function of s, and how we did it is we use linearity to get Laplace inverse of the smaller pieces, and these smaller functions of s, right, they just came directly from the table, right? Okay, so now let's consider this case here, right, where I have this function of s, right? Okay, and this function of s, and in particular, if you look at the denominator here, this s cubed plus 9s, right? This function over here is not going to come directly from your table, right? Okay, so what we're going to do to work this out is we're going to use partial fractions to break it up into smaller pieces and break up this y of s so that it's in smaller pieces such as this over here, right? And we're going to do that using partial fractions, and the idea now is that the smaller pieces, right, the smaller functions of s, those are going to come, you can take Laplace inverse by just using your table directly, right? Okay, so first we'd need to use partial fractions to split this up, right? Okay, so how would you use your partial fractions? Well, it's just, this is your standard method of using partial fractions, which you would have seen when you did integration of rational functions. Or rational function is you have a polynomial on top and you have a polynomial below, right? So a fraction with a polynomial on top and a polynomial below, right? Okay, so you should have seen integrating something like this, and the approach that we're going to use for taking an inverse Laplace transform is somewhat similar. First thing you're going to do is you're going to break it into, use partial fractions to split it up, right? And when you're using the partial fractions, what you want to do is the very first thing that you would do is you check to see if your power on top is higher or lower than the power below, right? And the first thing when you're using partial fractions is you look at the highest power on top and the highest power below, right? And if the highest power on top, okay, is larger than, is greater than or equal to the highest power below, right? Then what you do is you do long division of polynomials, right? Which you probably would have seen already. Okay, and once you do that, right, what you will get is an expression. You get a polynomial and then you'll get a fraction, right, where the power on top would now be lower, right? Okay, so you deal with your highest power on top being greater than or equal to your highest power below, right? But the cases that we would look at when we looking for inverse Laplace transforms, right? The highest power on top, in this case 2, would pretty much always be less than the highest power below, right? So notice here I have 2 and here I have 3, right? So there's no reason for long division of polynomials over here, right? Okay, so right, so once we establish that, right, next thing is in order to use your partial fractions, right, what you'd need to do is you need to factorize the denominator, right? Okay, so that's the first thing you'd want to do, right? And here you realize I can pull an s out, so I get s on s squared plus 9, right? Okay, now this here, this s squared plus 9, it can factorize some more, right? But in order for this to factorize some more, you'd need to use complex values, right? So here, this, if you wanted to factor this some more, what you'd have is s plus 3i times s minus 3i, right? And we don't want to do that in this class, right? Probably in your other courses, you may factor into linear factor with complex roots, right? But we're not, as far as this s squared plus 9 is concerned, this is irreducible, right? So we're not going to factor into linear roots, right? So when we factor in, we factor into linear factors such as this s over here and then quadratic factors, right? The way you're going to keep this quadratic factors in this form is when you have complex roots, right? So if you try to factorize this, right, and you're just getting complex roots, right, then what you do is you just leave it as it is, as the s squared plus 9, right? Okay, so now that we have the factors in the denominator, right, so you factorize in the denominator, not the numerator, you factorize in the denominator. The form of your partial fraction expansion depends on the factorization of the denominator. Okay, so in this case, the form of your partial fraction expansion has to do with the fact that you have a linear factor here, s, and then a quadratic factor, s squared plus 9, right? So if you have a linear factor, right, which is the s here, you're going to have constant, some constant, and you call that constant big A over the s, right? And if you have a quadratic factor, you're going to you have two arbitrary constants here. So the form on top here would be bs plus c, right? And then your quadratic factor would be s squared plus 9 on the bottom, right? So this partial fraction expansion depends on the factorization of your denominator here, right? Okay, so if you want a next example of the form of your partial fraction expansion, let's consider this a little more complicated example. Here, what I have is I have partial fraction expansion. Sorry, I have this rational function over here, right? And the form of the partial fraction expansion would be based on the factorization in the denominator here, right? So here I have a quadratic factor, and I have a repeated linear factor, s minus 2 squared, right? Okay, so your partial fraction, the form of your partial fraction expansion for this case, right? Again, what you're going to have is for your quadratic factor in the denominator, you're going to have constant times s plus an x constant, like what I have over here, right? But once you have repeated linear factors, this would be the form of the partial fraction expansion that you'd use for repeated linear factors, right? So you're going to have a partial fraction for each power, right? So here I have it's s minus 2 squared, so I'm going to have one for s minus 2. Then I'm going to have one for s minus 2 squared, right? And in both cases, what I'll have is I'll have a constant on top here, right? So for the s minus 2 squared, I'm going to have one partial fraction, which is a constant on s minus 2. And then a next fraction, which is a constant on s minus 2 squared, right? And that's essentially how you're going to deal with repeated factors, right? So let's see our next example of this. Okay, so for this function of s here, the form of the partial fraction expansion would be based on the factorization in the denominator. Here, it's two different linear factors, both repeated, this one to the power 3 and this one to the power 2, right? Okay, so for the s minus 1 to the power 3, you're going to have three different partial fraction expansions. Three different partial fractions, right? One for s minus 1, one for s minus 1 squared, and one for s minus 1 cubed, right? And in each of those cases, you're going to have a constant on top, right? Notice it's a different constant. They're calling it a1 over here, a2 over here, and a3 over here, right? Okay, so that's for the s minus 1 cubed. And for the s minus 2 squared, you're going to have two fractions here, right? One would be for the s minus 2 and one would be for the s minus 2 squared, right? And both of them have a constant on top here, right? Okay, and one, say, last example of this is, say, over here, right? Notice in this case what I have is I have repeated, but it's now the quadratic factors that are repeated, but it's a similar idea, right? So for the s squared plus 1 squared, s squared plus 1 all to be squared, right? I'm going to have one fraction, which is the s squared plus 1. And notice I'm going to have something times s plus a constant, just like across here, right, for that. And then I'd have a s squared plus 1 squared, right? So for this s squared plus 1 squared in my original function, I'm going to have two fractions, one for the s squared plus 1 and then one for the s squared plus 1 squared. And in both cases, I'd have a constant times s plus a constant. And in this case over here, I have constant times s plus a constant, right? Notice the different constants over here, right? Okay, so this is a linear factor, right, squared, right? And for this linear factor squared, what I would have is I'd have two fractions, one for the s plus 4 and one for the s plus 4 squared, right? And in both cases, I'd have a constant on top. Okay, so returning to example, remember what we're trying to do, right? We're trying to get the inverse Laplace transform of this function of s, right? And I said in order to do that, right, what I'm going to do is I'm going to use partial fractions to break this up, right? The form of your partial fraction expansion depends on the factorization in the denominator. In this case, I have a linear factor and a quadratic factor, right? Linear factor, you're going to have a constant on top here. For quadratic factor, you have constant times s plus an x constant, right? Okay, so once you get this form of your partial fraction expansion, now what you do is you clear your denominators, right? So you're going to multiply both sides of this expression by s on s squared plus 9, right? Okay, so what you do at this point here is you clear your denominators, right? So by clearing the denominators, I mean this denominator here, s on s squared plus 9, I'm going to multiply both sides by this s on s squared plus 9, right? So this expression here, which is s squared minus s plus 9 on the s squared plus 9 plus as plus bs plus c on s squared plus 9. What I'm doing is I'm multiplying on both sides by s squared plus 9, right? Okay, so this s squared plus 9 will cancel with the one on the bottom here, so I'm going to be left with just the s squared minus s plus 9 on the top here, right? And on this right hand side, right, the a on s will hit the s squared plus 9, and this s here will cancel with this s over here. So I'm left with big A times s squared plus 9, which is this here, right? And then the bs plus c on the s squared plus 9, right? The s squared plus 9 will cancel with the s squared plus 9. So what I'm left with is bs plus c on s, right? Okay, so notice the denominators are gone in this expression, right? So that's what I mean by clearing denominators. And now at this point in time, what you want to do is you want to figure out what your constants a, b, and c are, right? There's a couple of ways to do this. You could substitute values, right? Or you could compare powers of s, right? In this case, it's easier to just compare powers of s, right? Okay, that usually happens when you have quadratic factors, right? If you have a quadratic factor. If you just had purely linear factors in the denominator here, it'd be easier to substitute values. Anyway, so let's just compare the powers of s, right? So in order to do that, what you need to do is you need to expand this out and then collect the powers, right? So notice here I have as squared and I have a bs times s. So I have an as squared and I have a bs squared, right? Okay, so as squared combined with the bs squared gives me a plus bs squared, right? And then I'd have a cs here, which is a cs. And then finally I have a 9a, which is this 9a over here, right? Okay, so what I did is I expanded out everything, and then I just collected the like powers of s, right? So I have s, a term in s squared, a plus b, a term in s, which is the c, right? And then 9a, I have a constant term, okay? Okay, and what you do now is you compare your powers of s, right? And you look at the coefficients, right? So the coefficient of the s squared on this side over here is 1. The coefficient of the s squared on this side is a plus b, right? And that gives me one equation. A plus b is equal to 1, right? Okay, now you look at the term in s, right? And the coefficient for the term in s on the left-hand side is minus 1, right? The coefficient for the term in s over here is c, right? So I have c is equal to minus 1, okay? And then finally, I compare the constant terms, right? So on this side over here, I have 9, and then on this side over here, I have 9a. So I get 9a is equal to 9, right? Okay, so what I have is three equations now, right? A plus b is equal to 1, c is equal to minus 1, and 9a is equal to 9. And you solve these, right? And usually for us, it's just best to just solve them by hand, right? You don't want to use, say, like your methods from 1180 where you form a matrix and so on, right? It's probably best to just do these by hand. These are usually simple enough, right? Okay, so I see that the c is equal to minus 1. I see that from this equation 9a is equal to 9, I have a is equal to 1. And if a is equal to 1 over here, then the b must be 0, right? Okay. Right, so I get a is equal to 1, b is equal to 0, and c is equal to minus 1, right? Now this was the form of my partial fraction expansion, right? So I just put these constants into the form of my partial fraction expansion. So a is equal to 1 over here, b is equal to 0, and c is equal to minus 1. What I end up with is this here. And this is my partial fraction expansion, right? Okay, and notice what it did is it broke this function of s over here into simpler functions, right? 1 on s over here, and then minus 1 on s squared plus 9. Okay, and now I can take Laplace inverse of this function of s, right? The part. Okay, and now Laplace inverse of my given function of s is the Laplace inverse of the partial fraction expansion of that function, right? Okay, and the individual functions inside here, the smaller ones, now just going to come directly from the table, right? Okay, so, but the first thing I need to do is I need to use the linearity to break this up, right? Okay, so I have Laplace inverse of 1 on s, right? And here, what I did is I realized, well, okay, this is s squared plus 9, right? So this here, I would need to use my formula for sine, right? Sine kt, right? So this is s squared plus 3 squared, right? But in order to have the 3 on top over here, because remember I have k squared here and k on top, right? In order to have the 3 on top, I multiply by 1/3, right? Out in front over here, right? With the effect that the 1/3 times the 3 will just give me back the 1, right? So this is the adjustment to the constants, this 1/3 and 3 business. This is the adjustment to the constant that I talked about a couple of minutes ago, right? Okay, so you use your linearity to break this up, and then I adjusted the constant on top over here by 3, and I pull the 1/3 out, right? And now these are just going to come directly from the table, right? Laplace inverse of 1 on s. Well, you actually see in it over here. Laplace inverse of 1 on s is 1, right? And then the Laplace inverse of the 3 on s squared plus 3 squared, right? The 3 on s squared plus 3 squared is sine 3t, which is this answer over here, right? So my required inverse Laplace transform is 1 minus 1/3 sine 3t. Alright, so what we want to consider now is something called shift in theorems, right? Okay, so what is a shift, right? So suppose I have a function f of x, right? And with a graph such as this, right? Okay, so this particular function is f of x is equal to x squared, and the graph, this is a graph over here, this parabola, right? Okay, so this is your original function f of x, right? And now what I want to do is I want to consider f of x minus a, right? So your variable inside here, the x is shifting, it's changing from x to x minus a, right? Okay, so this is a function to start off with f of x, right? And this f of x minus a is what we're going to call a shifted function, right? Now, why you call it a shifted function is if you consider, say, a graph of the original function, like this one over here, the f of x is equal to x squared, then the shifted function in this case, if f of x is equal to x squared, is when you replace x over here. Everywhere you see the x, you're going to replace by x minus 2, right? So this is an example of a shifted function. So if f of x is equal to x squared, f of x minus 2 is x minus 2 squared. And the graph of x, f of x minus 2, which is x minus 2 squared, would be a parabola such as this, right? And notice your vertex of the parabola moved from x is equal to 0 over here to x is equal to 2. Matter of fact, your entire graph, right? What happened to your entire graph? It got translated to the right by 2 units, right? Okay, so this is one reason why you'd call, if you have f of x, why you'd call f of x minus 2 a shift of f of x, right? Because if you look at the graph of the original function, to get the graph of the shifted function, you take the graph of your original function and you shift it by a certain amount of units, right? The amount of units you shift it by is this 2 over here, the amount that you in f of x minus 2, right? So this 2 over here is telling you how much to shift by. So as I just said, if you have a function, then what you could do is when you consider, if you have a function f of x, if you change your variable over here from x to x minus a, right, then your new function over here is a shift of your original function f of x, right? Now, what we're dealing with here is Laplace transforms, right? Okay, and with Laplace transforms, we have a function of t, right? And we also have a function of s, right? So the when you have your y of t and you take Laplace transform of it, you're going to get a function big Y of s, right? So what I'm saying here is that when we're doing shifting here, you could actually shift either the t variable or you can shift the s variable, right? And both cases there, right? They give you different formula, and those formula are useful, particularly when you take an inverse Laplace transform, right? So actually the main reason why we're doing the shifting formula, right, is to get a couple more formula that are useful when we take an inverse Laplace transform, right? Okay, so as I said, you could either shift s variable or you can shift t variable, right? And the first case that we will look at is when we shift in the s variable. The first case of shifting that we will look at is when we shift the s variable, right? So as I said, here what we're doing is taking Laplace, so you have functions of t and you have functions of s, right? And I can shift either one. And the easier case is actually when you shift s variable, right? Okay, so what is this shifting of s variable formula, right? Well, here I have my standard notation for Laplace of the small y of t is equal to big Y of s, right? Your convergence over here, doesn't concern us in this class, right? So you could not really concern yourself with the convergence over here, right? All we're concerned about is the formula for the Laplace and the Laplace inverse. Right, so standard formula here, Laplace of yt is equal to y of s, right? Okay, and one version of the shifting formula is if I have this y of t over here, and I multiply by exponential e to the at, right? Then Laplace of e to the at is y of s minus a, right? Okay, so notice Laplace of yt is y of s, right? And Laplace of yt times exponential e to the at is y of s minus a, right? So you in fact have a shift going from the y of s over here to the y of s minus a, right? Okay, or next way to look at this is if I have a function y of t and I take Laplace of it, right? If I take my function and multiply by exponential and then take Laplace, that would cause my original Laplace transform in S, right, to shift by A, right? Okay, and a next way to state this is equivalently, well, if Laplace of e to the at is equal e to the at times yt is equal to ys minus a, then Laplace inverse of the ys minus a is this function e to the at y of t, right? But y of t is Laplace inverse of y of s, right? So I get this expression here, right? Or you can read this that if I want to get Laplace inverse of y s minus a, something that is shifted, right? What I can do is I can unshift, right? So the s minus a, I'm just going to convert to s over here. Take Laplace inverse of that and then multiply by exponential, right? So it's easier if you see an example of this, right? So we'll do examples of both of these. All right, so I want to get Laplace of e to the 2t times t squared, right? And notice this one, this here, we don't really know how to do this from the table directly, right? We can get Laplace of t to the power n, right, using the formula here, or I can get Laplace of exponential, but this product over here is not the product exponential times t squared, right, is not on the left hand side of this table, right? Okay, so to work this out, we're going to be using this formula here of Laplace of the exponential times y of t, right, is ys minus a, right? Okay, so what we're doing is we're using this version of shifting s variable, and what this says, if Laplace of y of t is y of s, then Laplace of the exponential times y of t is ys minus a, right? Okay, so we want to just, well, what's the original function over here, right? The original function would be t squared, right? So it'd be the t squared, and then what you'd do is you'd multiply the t squared by exponential, right? So you'd have your original function t squared over here, and then you'd multiply your function t squared by exponential, right? Okay, and as I said before, right, don't worry about the convergence over here, just focus on the Laplace computations, right? Okay, so here what I have is I know that Laplace of t squared is 2 on s cubed, right? That is coming from formula for Laplace of t to the n, right? Okay, and what this implication is doing for me, what this formula is saying is that if I want to calculate Laplace of exponential times t squared, if I want to calculate Laplace of exponential times t squared, that would be basically the same as the Laplace of the t squared. But what you need to do is you need to take this and you need to shift it, right? Okay, so when you multiply by exponential, if you have your function y of t over here and you multiply by exponential and then take Laplace, right? What you do is you take your Laplace transform and you shift it by the coefficient inside here, right? So the coefficient in the e to the 2t is 2, right? So you shift from 2 on s cubed to 2 on s minus 2 cubed, right? So the s would shift to s minus 2, and that's this 2 over here, right? Okay, so this is a nice, if you have Laplace of a function such as t squared and you know it already, right, then really you can calculate Laplace of exponential times t squared by using this formula over here. All you need to do is you need to adjust it appropriately. And how you adjust it appropriately is you just, the s in the formula, you replace the s by s minus a, and in this case the small a is 2, right? So you replace the s by s minus 2. Okay, so let's see a next example of using this s shift formula here, right? Okay, so Laplace of cosine of 2t is s on s squared plus 4, right, from my table, right? But what I want now is Laplace of the exponential times the cosine, right? Okay, so if I have a function and I multiply it by exponential, right, how your Laplace transform is going to change is wherever you have the s over here, the s will shift, right? Okay, and it will shift to s minus 3, right? And where that 3 is coming from, so when you multiply by this exponential, right, it's e to the 3t, right? Okay, so the s is, if Laplace of cos t is s on s squared plus 4, right, then the Laplace of the exponential e to the 3t times cos 2t, right? How you get your answer is you, in this expression here for the of s on s squared plus 4, wherever you see the s, you're going to replace the s by s minus 3. Okay, and this is going to be your answer, right? So your answer is s minus 3 on s minus 3 squared plus 4, right? Okay, so again, what you're doing is you're using this formula here, right? So if Laplace of your original function is y of s, big Y of s, then Laplace of the exponential times the original y of t is you're going to get from the big Y of s, but you're going to replace the s by s minus a, right? So here, this is the big Y of s, and here, this is where you, in the big Y of s, you replace the s by s minus 3, right? So that's how you get this answer. Right, so shifting s variable, we have two formula, right? One for when we take in Laplace, right, and one when you take in Laplace inverse, right? And we just saw examples of using this first one over here when taking Laplace transform, right? Okay, so now let's look at this one over here when we take in Laplace inverse, right? Okay, so, well, how do you read this, right? If I want to get Laplace inverse of something that is already shifted, right, what I do is I remove the shift, right? So if you want, you could unshift, right? So you go from s minus a to just s over here, right? So Laplace inverse of the y s minus a is Laplace inverse of the y of s, but you need to multiply by exponential, right? E to the at. Okay, so let's see how that works over here, right? I want to get Laplace inverse of the 1 on s minus 2 squared, right? So you notice that this over here, this is shifted, right? It's of the form s minus 2, right? So what you do is you unshift, right? So you replace the s minus 2 by just s over here. Notice what you go is, this is somewhat complicated, 1 on s minus 2 squared, right? To something that is simpler, 1 on s squared here, right? Okay, so I have Laplace inverse of the shifted guy, right, is equal to exponential times the unshifted, right? So going from the 1, the shifted is 1 minus s2 squared, and the unshifted is 1 on s squared, right? I multiply by the exponential e to the 2t, and where the 2 comes from is this 2 over here, right? S minus 2, it's that 2 over there, right? Okay, and now once you reach over here, you have Laplace inverse of 1 on s squared. And what you do is you'd use your table, where what you're doing is you're using this formula for Laplace of t to the n, right? So Laplace inverse of 1 on s squared would come from your table over here, where you're using the small n is equal to 1, right? Okay, so the idea here is that while this is a little complicated, by changing the s minus 2 to just s, right, it becomes simpler, and now you can work it out from your table. Okay, so let's see our next example of using this shifting formula, right, in the case of inverse Laplace transform, right? So I want to get Laplace inverse of this, right? Now this one is particularly useful, right? Because what I want to do is I want to get Laplace inverse of 1 over a quadratic, right? And if you want to notice in your tables over here, your quadratics in the denominator, it's s squared plus a constant or s squared minus constant, right? Notice over here what I have is now I have a term in s, right, which is not present in, say, like s squared plus k squared, right? Okay, so how you deal with that is first you complete the square, right? And completing the square means that you're going to divide the coefficient of the s over here, which is minus 2, divide that by 1. So you're going to get s minus 1 squared, and then when you expand this out, you would have s minus 2s plus 1, right? So that extra plus 1 you need to subtract from this 10 over here, right? Okay, so going from here to just completing the square, right, you're going to divide your coefficient of the s by 2, right? So you're going to get s minus 1 squared. And you'd need to subtract this number minus 1 squared, right? So 10 minus 1 squared, right, is 10 minus 1, which is 9, right? So this is just standard algebra completing the square, which you should know already, right? Okay, and completing the square takes me from s squared minus 2s plus 10 on the bottom to s minus 1 squared plus 9. And now what I want to do is I want to get Laplace inverse of this, right? Okay, so notice this over here, this is of this form ys minus a. This is a function of s that has a shift in it, right? Okay, and we're going to apply this formula. So applying this formula means that I need to unshift, right? So I'm going to, the s minus 1, I'm just going to convert to s, right? When I do that, I multiply by a suitable exponential, and the coefficient in front of the t over here is 1, right? So I have e to the t, right? So then e to the t Laplace inverse of 1 on s squared plus 9. And now you just use your table to work this out, right? The s squared plus 9 you will get from 1 on s squared plus 9 you'd get from using your formula for Laplace transform of sine kt, right? This is 9, which is 3 squared. I'd want a 3 on top here, which means I'd need to adjust by a constant 1/3. Okay, so I get 1/3 e to the t Laplace inverse of 3 on s squared plus 3 squared. And Laplace inverse of this is sine 3t, right? So my final answer is 1/3 e to the t sine 3t. Right, so let's talk about shifting t variable now and the formula that we will get from shifting t variable, right? Okay, but before I get into shifting t variable, what I need to do is I need to talk about Heaviside step function. Right, okay, so your Heaviside step function is a piecewise defined function, right? It's ht minus t0, right? And that t0 is some constant time value, okay? And what your Heaviside step function, what is happening is that it's going to be 0 before that constant time value t0, and then it's going to be 1 afterwards, right? So this is the definition over here as a piecewise defined function. Your function is equal to 0 before t0 and is equal to 1 at t0 and for all values after t0, right? So you add 0 and then you step up to 1, right? In some textbooks and in some diagrams you'd see that it's 0 over here and then you'd step up to 1 and then they would include this vertical line over there. Now strictly speaking that really isn't correct. It does help you see the step, right? The fact that it's stepping from 0 to 1, right? But strictly speaking you really shouldn't have a vertical line like this, right? Because it means that your function is undefined at well, in this case t is equal to 0, right? Okay, so but anyway, the idea is that your Heaviside step function is 0 before time t0 and t0 is some constant time and then 1 afterwards, right? Okay, now this being a piecewise defined function, you should actually know how to get Laplace transform of this, right? Okay, and the proof is in the notes, but what I really want you to get out of this is that the Laplace transform of your Heaviside step function is e to the minus st0 on s here, right? So this is a formula for Laplace of Heaviside, and that's typically given in your tables as well, right? So you see in Laplace of your Heaviside over here is e to the minus st0 on s here. Okay, so your formula for shifting t variable would be these formula here. So similar to shifting s variable, you have a version for Laplace and you have a version for inverse Laplace, right? Now notice that both of these involve this sort of expression over here, which is a Heaviside times a function of t, and this function of t is shifted, right? Okay, so an example of a function, this Heaviside times a function yt minus t0 is this y of 3t over here, right? Which is a Heaviside ht minus 2 times sine t minus 2, right? Okay, so what I'll talk about is I'll talk about what this is over here, right? And so it'll give you an idea what these types of functions are, right? What the type of function Heaviside times yt minus t0 would look like, right? Okay, so let's consider this example here. I have three functions, right? Sine t for t bigger than or equal to 0, sine t minus 2 for t bigger than or equal to 2, right? And then this function over here, which is sine t minus 2 times your Heaviside ht minus 2, right? So notice I have three functions over here. I call first one y1, second one y2, and third one y3, right? Okay, so sine t for t bigger than 0, well, you all know what sine t is going to look like. It's a sinusoidal, right? It's defined for t bigger than or equal to 0, right? So this, what I have over here for y1 of t, you want to be a little careful. It isn't just sine t. It's only the part of sine t when t is bigger than or equal to 0. And actually y1 of t is not defined for t less than 0, right? Okay, now we have sine t minus 2, right? So how you'd get your graph of sine t minus 2 is you take your graph of sine t and you shift it forward by 2 units, right? Which is what happens over here, right? So this is sine t and this is sine t minus 2, right? But notice what the y2 of t is, right? y2 of t is sine t minus 2 only for t bigger than equal to 2, right? So it's as if you took your graph of sine t, you shifted it forward by 2, but you only taken the part of the graph that is for when t is bigger than equal to 2, right? Now, what you want to notice about y2 of t is y2 of t is defined for t bigger than equal to 2, but it's actually not defined before 2, right? And that is just how it's constructed, right? Okay, why have it as undefined for t less than 2 in this definition over here is to illustrate a point in y3 of t, right? Okay, so now what I want to do is I want to get an idea what this looks like, right? So the sine t minus 2 times the Heaviside, right? Okay, so I want to get an idea of what this is, right? And how I'd get an idea for what this is I'm going to construct a table to give me an idea what the values of this function is going to be, right? Now this has a ht minus 2 in it, right? The Heaviside t with Heaviside t minus 2 over here. So what this means is that if you're just looking at the Heaviside alone, right? The Heaviside alone would look like this, where the change in behavior is at time t is equal to 2, right? So ht minus 2 is going to be 0 before 2, and then it's going to be equal to 1 after 2, right? Okay. Right, so ht minus 2, we can actually put this in a table, right? And for values of t that are less than 2, for values of t that are less than 2, so between 0 and 2, the Heaviside is equal to 0, right? So between 0 and 2, the Heaviside between 0 and 2, the function value is equal to 0, right? And then after 2, the function value is equal to 1, right? So that's where this comes from, right? And now what I want to do is I want to consider this ht minus 2 times sine t minus 2, right? Now, if the ht minus, and then I want to consider ht minus 2 times sine t minus 2, the values on the two intervals, right, from 0 to 2, and then 2 onward, right? Now, between 0 and 2, the Heaviside is equal to 0, right? So that would mean the product of the Heaviside times the sine between 0 and 2. The Heaviside is 0, and 0 times the sine would just give me 0, right? And then for t bigger than or equal to 2, right, the Heaviside is going to be equal to 1, right? So your product over here, Heaviside times sine, when t is bigger than or equal to 2, it's going to be 1 times sine t minus 2, which is just sine t minus 2, right? Okay, so if I'm looking at this expression, ht minus 2 sine times sine t minus 2, right? And I consider your two intervals from 0 to 2, and then from 2 onward, right? From 0 to 2, this product, ht minus 2 sine t minus 2 is equal to 0. And then after 2, it's equal to sine t minus 2, right? And we saw what sine t minus 2 looks like, right? It's the graph of sine shifted forward by 2, right? Okay, so if you compare this one over here, which is the y2 of t, to this one over here, you want to notice that they're basically the same thing, right? The only difference is that this y2 of t is not defined between 0 and 2. But this one over here is defined between 0 and 2. Otherwise, they're basically the same, right? Okay, so what I want you to get out of this is this ht minus 2 times sine t minus 2 is essentially just a shift of the sign, right? It's just a shift of the sign. You take the sign, you shift it forward by 2, and you get this piece, right? So this ht minus 2 times sine t minus 2 is really just a shift of the sign function, right? And one thing that you're doing is when you shift it forward by the 2, right? The gap over here, you're just filling it in with 0 here, right? So you could just really think of this ht minus 2 times sine t minus 2 as just a t shift of the sign with an additional piece of information that between 0 and 2 your function is equal to 0. Alright, right, so now I want to consider my t-shift formula, right? And as I said, you have two versions of it, one for taking Laplace and one for taking Laplace inverse, right? Okay, so let Laplace of small y of t be equal to big Y of s, right? So this is your standard notation, right? And what one t-shift formula is saying that Laplace of the Heaviside times the shifted small y, so yt minus t0, right, is going to be equal to the Laplace transform of just the yt. So okay, so this yt minus t0 is shifted, the yt is unshifted. So the Laplace transform of the Heaviside times the shifted one is equal to the Laplace transform of the unshifted one, right, times an exponential, right, e to the minus st0, right? And this t0 constant over here is this t0 that's showing up in your Heaviside here, right? Okay, or the next version is, and this is the one that we would use in this class, right, is that the inverse Laplace transform of e to the minus st0 y of s, right, is equal to Heaviside times yt minus t0, right? Okay, so how this one is working is if I want to get Laplace of e to the minus s t0 times y of s, what you're doing over here is you consider the y of s over here, the big Y of s. You take the inverse Laplace transform of that to give you the small y of t, right? And then you shift that by t0, right? And then finally you multiply by ht minus t0, right? Okay, so it's probably best if you just see an example of that. Alright, so we want to get Laplace inverse of this function of s, and notice it has an e to the minus 3s in it, right? Now this here, this sort of function of s is not something that we saw in our table, right? So you're not seeing e to a power s over here, right? Or e to, the only place that you see in it, well, it's actually these here, right? It would only be these two that we would consider in this class. We will not do Dirac delta in this class, right? Okay, so this, when you have a e to the minus s on top, you need to handle it appropriately. And typically what we do to get an inverse Laplace transform of something with e to the minus s, such as this e to the minus 3s in it, right? We're going to be using this, well, the answer is going to be a Heaviside times yt minus t0, right? In other words, what we're going to be doing is we're going to be using this formula for the Laplace inverse, right? Okay, so if you're using this formula for the Laplace inverse, right, what you need to do is you need to identify key points in this formula, right? So what are the key points in this formula, right? The key point is the t0 and the big Y of s, right? Okay, so this is the formula stated over here, right? And what I want to do is I want to get Laplace inverse of e to the minus 3s on s squared plus 1, right? Okay, now you want to notice how this is written, right? This is written as e to the minus st0 times a function of s, right? And this over here is not quite written in that form, right? So what you need to do is you need to rearrange the inside of this Laplace inverse so that it is of the form e to the minus 3s times a function of s, right? Okay, so now this e to the minus 3s on 1 on s squared plus 1 is of this form over here, right? And I can identify what the y of s is, right? The y of s is this 1 on s squared plus 1, right? Okay, and I can also identify what the t0 is. The t0 is the coefficient here for the minus s, so the t0 is 3, right? Okay, so so I identified what the big y of s is, and I identified what the small t0 is, right? Small t0 is 3, and the big y of s is 1 on s squared plus 1, right? Okay, so the idea over here is that when you want to take Laplace inverse of this, right, from the big y of s, you get the small y, and that small y you need to shift, right, and then multiply by a Heaviside, right? So from the big y here, right, right, what I need to do is get the small y, right, because in this notation, if I have the big y of s, the small y of t is the inverse Laplace transform of the big Y of s, right? So that's what the small y is, right? Small y over here is the inverse Laplace transform of the y of s, right? Okay, so this is the big Y of s, right? I need the small y of t, and the small y of t is the inverse Laplace transform of the big Y of s, right? That is really just from this over here. And that tells me that the small y of t is Laplace inverse of 1 on s squared plus 1, which is sine t, right? Okay, so given this y of s, first thing I need to do is find the small y of t, right? But what I have in this formula here is small y of t but shifted, right? Okay, so what I need to do is I need to shift the small y of t, and when I shift the small y of t, I go from sine t to sine t minus 3. Anyway, so let me just write down what I have so far, right? So Laplace inverse of this expression, I'm going to be using this formula here, right? I figured out what the t0 is. The t0 is 3, right? So the t0 is 3, right? So I'm going to be using this formula where the t0 is 3. And all I need now is the small y t minus 3, right? But we already figured out that the yt, the small yt, is sine t. So to get the yt minus 3, all you do is wherever you see the t over here, you replace the t by t minus 3, right? So yt minus 3 is going to be sine t minus 3, which is what I have over here, all right? Okay, so one more time, right? When you're using this type of formula for Laplace inverse, first thing you need to do is I need to identify the big Y of s, right? Big Y of s, and you need to rearrange it if necessary so that you can identify the big Y of s. The big Y of s is 1 on s squared plus 1, right? And then from this big Y of s, you take the inverse Laplace transform of it to get the small y of t, right? Which is your sine t over here in this case, right? Also, you need to identify the t0, which in this case is 3, right? And then finally, your Laplace inverse is ht minus 3, right? Small yt minus 3. And now all you need to do is figure out what the small yt minus 3 is. And you should have figured out what the y of t is from before, from the y of s, by taking inverse Laplace transform. And then finally you just shift that small y of t to yt minus 3 to get you your answer.